Hello, can everyone hear me?
Yes.
Awesome. Sorry, I'm just turning up my volume a little bit. Do you get an echo if you talk?
No.
Okay, let me know if you do, and I will fix that. Just before we start, could I get everyone's PSU ID in the chat? Just your, basically your email, like the letters and the numbers. And again, that's just for me to take attendance so that my bosses know that people are coming to these sessions. Okay, thank you very much, guys. Okie doke. So this week we were talking about derivatives of inverse functions, derivative of logarithmic functions, and then the inverse trig functions. This is kind of like a interesting section to go through, especially because I'm pretty sure that we didn't do this in like years previous. Like go into chapter 6 in the way that we have. You guys weren't responsible for any of that integration stuff, right? Like you could just ignore that, is my assumption. Because that would be a lot to spring on you right away. And I just skipped past my chapter. Oh, darn it. Where's chapter 6? There it is. Okay. Let's just get right started in 6.1. And let's start with number 3, where we have a table. I am on page 406, by the way, where we have a table that looks like this. We have x, and then we have the function f of x, and we have a series of values. And we are tasked with determining if this is a one-to-one function or not. So let's first ask, what does it mean for a function to be one-to-one? Any ideas? Yes, essentially, yeah. So what can you tell me about this?
It has two of the same f of x values, so it's not one-to-one.
Does, exactly. We have x is equal to 6 and x is equal to 2, and they're both equal to 2.0. So this is not 1-to-1. What about if we looked at a graph? For instance, number 6. Didn't mean to do that in red. Number 6. We have a graph that looks a little bit like this. Here's our x-axis, here's our y-axis. What do you think about this one?
I guess it could be, it could not be. It depends
Here
on
it's
if
not
this is
flat.
square.
It's just, yeah.
Okay, so if that's not flat, then it is one-to-one.
Yeah. Unfortunately, because of my drawing skills, there will be some discrepancies. But yes, this is a one-to-one function because theoretically we would be able to do the horizontal line test, and at all of these points it would touch that's not quite horizontal, but it would touch just one point on the line. Okie doke. What about for number 9? Is this a one-to-one function? Why do you think that? It's linear, exactly. I've got a line going that looks something like this, and lines are going to be one-to-one. Awesome. What about if I had a function that looked like, let's do number 15, where we have f of t is the height of a football t seconds after kickoff. What would the shape of this function be?
It would be an upside down U.
Yep. It would be a parabola. It would look something like this, where here the football is kicked, and here is where it lands. This is time. Is this one-to-one?
No.
Nope. Because the only point where it is only that height once is the maximum. And then after that, there is always when it's going up and when it's coming down. Okie doke. You guys seem to be doing really great there. Let's try, let's maybe do one of the, like, using like derivatives. Let's try number 39. Here we have the function f of x is equal to 3x cubed plus 4x squared plus 6x plus 5. And we want to find f to the -1, or the inverse rather, prime of a, and here a is equal to 5. So walk me through this. What am I going to do to try to find the inverse derivative here? Where are you thinking we should start? Okie doke. So got 5. What are we thinking?
We move 5 on each side, yeah.
Okay. What's next?
We got factor an x out.
We could, but we know that this is all equal to 0.
Okay.
What is x going to be equal to if I've just got a series of x's added to one another? If x equals 0, then this is 0 plus 0 plus 0, right? And even up here, we could have made that statement because we have this 5, we have this 5, and I can see that if I zero that all out, then I'm going to end up with 5. So the statement that I want to end up making is that f of 0 is equal to 5. Are we good with that?
Okay.
And that's just like kind of making assumptions. It's a little bit of like jumping around, but it saves you from having to do all of that factoring, because it's what we're going to end up with if we just have a 0 here. So we have f of 0 is equal to 5. which we can use to say that the inverse is equal to, the inverse of 5 is equal to, the inverse of x of 5 is equal to 0. Okie doke. Does anyone remember the kind of setup that I'm going to do here to find what I actually want, which is the derivative of the inverse of a? Yes. So I'm going to have the inverse derivative of a is going to be equal to 1 over the derivative of the inverse of a, which in this case is going to be equal to 1 over f prime of this right here, which is equal to 1 over f prime of 0. Okie doke. So we have 1 over f prime of 0. That means we're going to need to find f prime of 0. How do I find f prime of 0? What do I do first to find f prime of 0? Yes, I'm going to take the derivative. I'm going to say that this is f prime of x, and that is 9x squared plus 8x plus 6 plus 0 now. And then I'm going to say that f prime of 0 is going to be equal to 0 plus 0, because I have 9 times 0, 8 times 0 plus 6. So my answer here is going to be 1 over 6. Does that make sense? Awesome. Okay. We have 3 sections to kind of book through today. Do you guys want to do more on 6.1, or would you like to talk the other 2 sections? It's up to you.
I'm good with anything.
Okay, let's do some questions from 6.4, and we can maybe come back if that's something you guys want to do.
Sounds good.
Okie doke. Scrolling to 6.4. Okay. So I am currently on page 436 in section 6.4, and we are going to start differentiation of logarithms. And we're going to jump right in with number 2. We're going to have f of x is equal to x ln x minus x. Okie doke. What do you guys see here? Like, what is your strategy for differentiation going to be? I mean, we could implicitly differentiate. We could say that this is going to be equal to y. And the principle here is that if I implicitly differentiate here, right, then I'm going to end up with the derivative with respect to x of x ln x minus x is equal to dy dx. So a lot of the times when we were thinking about like implicit differentiation, in section 2.6, we were looking at functions where we had like 9 is equal to x squared plus y squared. And we didn't want to have to solve for y and then differentiate with respect to x. So we can just think about this as differentiating with respect to x here, if that makes sense. Because essentially every type of differentiation we do is implicit differentiation. We just have it set equal to y so that we can find dy dx right off the bat. Does that make sense? You can say no and be okay. So what type of like differentiation strategies do you kind of think that we might use here? What parts do you see? Yep, we're going to need the derivative of the log. I am reading this. I feel like they would have put parentheses here if this was like x minus x. So it's rather this chunk here minus x. So we know that we're going to be able to use the derivative of a sum is the sum of the derivatives, right? So what I need to find is the derivative of x ln x minus the derivative of x, which is going to be easy. We know that. So when I have something that's set up like this, x ln x, what type of rule am I going to use to solve it? What is it? Like at its most basic, like am I going to use the chain rule? Am I going to use the quotient rule? Am I going to use the product rule? Is basically what I'm asking. That is true, yes. But I'm going to need to start with like analyzing what rule I'm going to use because I have x times the natural log of x, which means I've got a product, right? If I think about this as times exactly. So I'm going to have, I'll call it g of x is equal to x, g prime is equal to 1, and then I'll have h of x is equal to the natural log, and h prime is equal to, as you said, 1 over x. So I can put this together and I can say via the product rule that this is going to be equal to x times 1 over x plus 1 times the natural log of x. And then I can say that this, the derivative of x, is going to be 1. So to put this all together, I have got the derivative of f of x is going to be equal to x times 1 over x plus 1 times the natural log of x minus 1. X over x is going to be equal to 1. And then these ones are going to cancel out. So we're still going to be using the product rule, the chain rule, the quotient rule, and all of these problems. It's just a matter of figuring out where to use them. Okie doke. Let's do problem 5. Here I have f of x is equal to the natural log of 1 over x. What type of rule should I use here? What are we seeing? Chain rule, exactly. What is my inside function? Yep. So I'll call this h of g of x So h of g is going to be the natural log of g. So h prime of g is going to be 1 over g. And then I have g of x, which is equal to 1 over x. And what is g prime? Could use the quotient rule, or I could just rewrite this as x to the negative 1, and then we could use the power rule. We'd end up with minus x to the minus 2, which I guess I could write if I wanted to as 1 over x squared minus 1 over x squared. Does that make sense? Awesome. Okay, then I basically just need to put it together. I know that my derivative is going to be equal to h prime of g times g prime. So I'm going to be looking at 1 over my original function, which is 1 over x, or I'm going to write it in this case as x minus 1, times my derivative, which is going to be minus x minus 2. Stuff is going to be flip-flopping around here, essentially. So 1 over x is going to be equal to x. And this, now I'm going to write like this. I'm going to say that this is minus 1 over x squared. So this is going to be x over x squared. That's going to cancel with that. So I'm going to end up with minus 1 over x. Okie doke. Questions, comments, or concerns? What was that?
I think I got it. I struggle with this stuff a little bit, but I think I'm good.
Yeah, like all derivatives, it's just a lot of practice. And always remember, you fall back to your major rules. You know how to use the product chain rule and quotient rule. You can do that like 100%. Just identify what the functions are and where you need to use them. Okie doke. Let's do, let me see, I had written down number 14, but number 15 looks a little bit crazier. And my philosophy, at least in practicing these, is if you practice the really, really hard ones, you'll get so good at doing them that doing the easy ones is a piece of cake. And I, for the sake of handwriting, my n's and u's look very similar. So this is a function f of u. I'm going to rewrite it as the function f of x so that you guys are actually capable of reading it, because my handwriting gets really rough. So, okay, there's a lot of parts here. Right off the bat, what rule are we going to end up using? Quotient rule, yep. So we're going to call that, I guess, h of x. H prime of x is, as we said earlier, the derivative of the natural log of x is going to be 1 over x. Then we have here, we'll call this g of x. So g prime of x is going to be the derivative of 1 plus the natural log of 2x. What is the natural log of 2x? How would we find that? Well, I would recommend working through, at least very quickly, working through the chain rule. Saying that if I have my original function is, we'll call j of k, which is the natural log of k. J prime is equal to 1 over k. I have my k of x is equal to 2x. K prime of x is equal to 2. I have to put this together in the form j prime of k times k prime. So this is going to turn out to be 1 over 2x times 2. So it's going to end up being 1 over x. Yep. So just running through that all, just to be sure, we want to make sure that we're not confused or doing something incorrect. If you have time on exams, I would recommend working it all out. If you don't, then you can kind of like do a little bit of it in your head and work out like, hey, it's probably going to be 1 over x, but it's always good to just check and make sure. Okay, so knowing that the derivative of the natural log of 2x is going to be 1 over x, we now have the derivative of 1 is going to be 0, and the derivative plus the derivative of the natural log of 2x, which is 1 over x. So now we have each of our components. Does anyone remember what the quotient rule is? I always forget which one is subtracted on top. Anyone remember? Is it f prime, or in this case, h prime g minus g prime h? Or is it one of my fatal flaws? It is g h prime minus g prime h over. Okay, that makes sense. Yep. Over g squared. So that's what we're looking at for in terms of the rule. So g is going to be 1 plus the natural log of 2x times h prime is up here, it's 1 over x, minus g prime, which is 1 over x, times h, which is the natural log of x, all over g squared, which is going to be 1 plus the natural log of 2x squared. And I would leave it just like that on the bottom there. So yeah, you could factor out this 1 over x. You could say something along the lines of this is 1 over x times 1 plus the natural log of 2x minus the natural log of x over, again, 1 plus the natural log of 2x squared. And then this 1 over x could be, that's just x to the minus 1. So it could just be x down here. And that's probably how I would leave this answer. There's really not much more simplifying that I can see that would make this a more palatable answer. So you could expand that in the bottom using FOIL, it wouldn't really help. So this is how I would answer this on an exam. Any questions? Okay. Let's also do another one I thought would be a good one to practice that looked pretty grody, is number 22, which looks like this. We have the function h of z is going to be equal to the natural log of square root a squared minus z squared over a squared plus z squared. So there's just a lot of layers to this. Where would you guys like to start? How I would approach this is, yes, I would start setting up that chain rule. So I would say here I have f of g, which is the natural log of g. I have my f prime of g, which is 1 over g. I have my function g of, what is g a function of? What is my variable here? It's just an important thing to keep track of in a problem like this where you have both a and z. Both of them are not variables, only z is the variable. So a is going to be a constant this whole time. So g of z is going to be equal to, let's see if I squish my book just a little bit more. A squared minus z squared over a squared plus z squared to the half. Now, how would I end up finding g prime? I would actually break it down again. I would say that g prime is equal to, sorry, we're going to go through a lot of letters. We're going to like blow through like half the alphabet here. We'll call that, again, we'll have j is a function of k. So j of k of z, where j is going to be equal to k to the half. So j prime is going to be equal to 1/2 k to the minus 1/2. And we're going to have k, which is going to be a squared minus z squared over a squared plus z squared. So this is a function of z. How do we find k prime? Well, we've got a quotient here. So this is the function m of z over the function. We will call it r of z. I give them all different names and different colors so that I can keep track of them better and I don't get confused between them. If it makes it more stressful for you to do that, then don't do it with different names. But I do like to keep them organized in this way. So we're going through all of this so that we can end up with plus. Nope, that's, yes, it is a plus. I'm just not looking at it right. So that will be 2c. Is everyone following me up to here? I know there's a ton of junk going on.
Yeah.
Okay. So this is actually the derivative of this, which we can find by, again, saying this is going to be m prime, so minus, let me do this a little bit over here, minus 2z times a squared plus z squared minus 2z a squared minus z squared. And this is going to be over a squared plus z squared. I would distribute this out to see if I can get anything to simplify out, because I'm really hoping that it won't be this nasty the whole way through. So this is going to be minus 2z a squared plus, or rather minus 2z cubed minus, I'm going to put this as a quantity, 2z a squared minus 2z cubed. So this is minus 2z a squared minus 2z cubed minus 2z a squared plus 2z cubed. So I cross that off. And this is minus 4z a squared. Unless I screwed that up, and I don't think I did. Okie doke. All right. So this will give us k prime of z is equal to minus 4z a squared. And that is going to be over, I don't think that will help. So I'm going to leave it as a squared plus z squared squared. Okay. I'm going to clean up a little bit going on down here. Now I know what my k prime is. I know how to find, I found k prime. Now I have all of the components I need to find my original g prime, right? Where g prime is going to be equal to, as we said, j prime of g, or rather j prime of k, times k prime. So this is going to be 1 half times the original k, which in this case is going to be a squared minus z squared over a squared plus z squared, times minus 4 z a squared over a squared plus z squared squared. And this is to the minus 1 half. So there's my g prime. So is everybody following me all the way up through here?
Yep.
Awesome. This is essentially just a lot of algebra and putting things together in a very awkward way, but we can break it down in this way. Now to find our final answer, which we're going to say is h prime of z, we're going to need to use the chain rule again. So this is going to be 1 over g times g prime. right? Because I wrote it a little bit different way because I didn't want to write down everything quite yet, but I just said this is f prime, which is 1 over g times g prime is how we're going to find our answer via the chain rule. So this is going to end up being, I'm going to write it 1 over something to the 1/2 is equal to that thing to the negative 1/2, right? Like if I have 1 over x squared, that is equal to x to the negative 2. So in that same line of thought, I'm going to write down this as a squared minus c squared over a squared plus c squared to the negative 1/2. That negative is going to come from this green there. Then that is going to be multiplied by, I'm going to erase some of this because we got that. So that is going to be multiplied by 1/2 times a squared minus z squared over a squared plus z squared to the negative 1/2 times minus 4z a squared over a squared plus c squared. The way that this is going to simplify is that here we can basically move this 1/2 out, right? Because this is 1/2 like times. So I'm going to say this is 1/2 on this side. I'm going to move it so that I can look more closely at these two that I'm multiplying together, which are the same thing, right? So how do I do that? With my rules of exponents. If I multiply x squared and x to the 1, what am I going to get? You can always think about this and like, this is a simple thing. Like, I'm going to simplify this down. What does it look like if I just use my simple rules of exponents? It's going to be x to the 2 plus 1, right? So, because I'm multiplying two of the same thing, this is going to be a squared minus z squared over a squared plus z squared to the negative 1/2 plus negative 1/2, or to the negative 1. So this is 1/2 times 4 minus 4z squared over a squared plus z squared. There's more that we can do to basically simplify this out. I see I have a negative 1 here, which basically means this is 1 over each of these things, right? So this in the red, I'm going to turn into this in the dark red. So it's going to be 1/2, I'll leave that, 1/2 times a squared plus z squared over a squared minus z squared, right? Because basically what I did is I said, okay, so this is 1 over a squared minus z squared over a squared plus z squared, and what I can do is I can just move that back up to the numerator. So now I have this function, which matches up with what I have down here. And so this is I'll put the minus sign out here. I'll put the 4 out here too. So this becomes ZA squared over A squared plus Z squared squared. This cancels. Which turns this into minus 2 times 1 over A squared minus Z squared times ZA squared over A squared plus Z squared. We multiply this all together, we're going to end up with minus 2ZA squared over A squared minus Z squared times A squared plus Z squared, which is going to be A squared times A squared is A to the 4th. A squared times Z squared is A squared Z squared. It's minus here. And then I'm going to have A squared times plus Z squared, so it's positive, so they cancel. And I'm going to wrap it up with minus Z to the 4th. And that is going to be my answer. Does everyone see the very long roundabout way that we went around doing that? It wasn't really invested in logarithms, but I think it was a good problem to do, generally speaking, because it really makes you like go through all of the steps. Okay, let's move on to 6.6 before we run out of time. I'm going to squish this over a little bit. Okay, so read the book. Going to 6.6. Scroll, sorry. Where? What color are we looking at? Let's start with that. Oh, I see. At the very beginning, yes. You could have done that. That would have probably made your life a little bit easier. Yeah, you were right in thinking about that. I didn't think about that until I was like about halfway through, and then I was like, well, we're kind of committed now. But that's a really good thought to have. Okay. Where did it go? Oh, 5, I'm sorry. Frantically searching for 6.6. Okay. We're thinking about derivatives of the inverse functions now. This is one of those things that I'm not really an enormous fan of, because a lot of this is just they want you to memorize what the like derivatives are, as they kind of did in the original trig functions section, and just power through them all. So in that same vein, I think we should probably look for some of the more complicated ones. So let's do let's do number 23, where we have y is equal to tan inverse of x squared. So let's start with that. What do we see here? What rule, what basic rule are we going to be thinking about using? chain rule, yep. So I'll say that f of g is equal to g squared, f prime of g is equal to 2g. Then I have my g, which I'll say is tan inverse of x. What is g prime? Yep. It'll be 1 over 1 plus x squared. That's just a rule that you get to memorize. So we put it together in the exact same way we normally do. We say this is 2 times the original g, which is going to be tan to the minus 1x times 1 over 1 plus x squared. So this will become dy dx is equal to 2 tan to the minus 1 x over 1 plus x squared. And that's about what you can do there. But there you have it. I forgot to mention what page I'm on. I am in section 6.6 on page 480. Okay, let's do 29. Here we have the function f of x is equal to x, the inverse secant of x cubed. What are we thinking? What rules are we going to be using? I see 2. Product and chain, yep. Here we have our product. I'll call this g of x is equal to x. We know what g prime is. And then we have h of x, which is equal to the inverse secant of x cubed. H prime is going to be, if we divvy this up into, we'll call it j again, it'll be j prime of k of x times k prime, where j is equal to, call it j of k, is equal to the inverse secant of k. What is j prime going to be? The inverse secant, 1 over root 1 minus x squared. The only thing we're missing there is a big old x right here. So it's 1 over x times the square root of 1 over x squared. If you do 1 over the square root of 1 minus x squared, it is the sine inverse. So just make sure that we get the exact thing right. Don't want to miss that x. Wait, this isn't quite. It is not 1 plus. It is not 1 minus. This is x squared minus 1. right? Yeah. I'm sorry, I also have to go back to check page 479 because these are just not stuff that I use on the regular. Fortunately, you get to memorize them, but it should be 1 over x times the square root of x minus 1. And that is that. 1 over x times square root of x minus 1. Okay, we got that. Then we will say that k is equal to x cubed. We have k prime is equal to 3x squared. And we smash it all together so that we can say that h prime is equal to 1 over, these shouldn't be x's, these should be k's here. Just because that's the language that we're using. So this is going to be 1 over, now it's x. It's 1 over x cubed. Now, x cubed squared is what? X to the 6, yep. This is 3x squared. I'm going to cancel out that x squared there and 2 of those 3 x's there. Okie doke. So, kind of grody. We get to put this together. We get to say that this is g times h prime. So that's x times 3 over x root x to the 6 minus 1 plus our original h, which is the inverse secant of x cubed, times g prime, which is 1. So we can see that this x is going to be up here, and it's going to cancel with this x. So we are going to end up with the final answer of 3 over root x cubed, or x to the 6, excuse me, minus 1 plus the secant, the inverse secant of x cubed. And that is our answer. And I don't think that you could simplify it any further than that. Questions, comments, and concerns? I do. If I have time, and like if you're on an exam and you're running really low on time, then cut corners akin to this. But separating it out and explicitly saying like, this is what my derivative is, this is where it has to go in. For instance, specifically here, if you see in this light green, this like mint up here, I have k appearing twice. And I need to make sure that it gets put in twice. And this is how I find it most helpful to keep track of everything. Mostly because my brain is kind of disorganized, I think. And so writing it down for me helps me put my thoughts into order. Yeah. There are small ones where you definitely don't need to do this. It's a little extra to do this on some of the small ones. I sometimes do it anyway, but feel free, if you are comfortable, to just like cut a couple corners on the small ones. But I would definitely recommend, if you have something that is like a chain rule within a product rule, not to do it all in your head. Okay. Before we wrap up, let's do one that is fairly similar actually to the one that we just did, but we're going to use what Philip mentioned at the end of the last problem, and we're going to make it a whole lot easier. And we're going to throw some trig functions in there to make it hard again, which is number 34, which is going to look like this. So it's the inverse tan x over a. This is the function of x. And then we have the natural log of, as we said, x minus a over x plus a. This is to the 1/2. Philip pointed out at the end of the last one that what we could have done in the beginning is, because this is a logarithm and this is an exponent, we could rewrite this whole thing as an x. And that makes our life a lot easier. We get to cut out one of the chain rules. So let's solve this. We get to break it down. I would break it down into this over here, where I would split it into, here I have, we'll call it f of x, rather f of g. It's a chain rule problem, as we kind of talked about earlier, where it is 1/2 the natural log of g. What is f prime of g? What is the derivative with respect to g of 1/2 times the natural log of g? We get to keep following all of the rules that we have been using this entire time regarding constants. So the derivative is going to be 1/2 times the derivative of g. So it is going to be 1/2 over 2g. Yes, exactly. So then we say g is going to be a function of x. It's going to be equal to x plus, or rather x minus a over x plus a, g prime of x. This is one of those instances where we might just be able to piece it together a little bit. It's going to be the derivative of the top, which is just going to be 1 times the bottom minus the derivative of the bottom times the top over the derivative of the bottom squared, or not the derivative, just the bottom squared. So I didn't write it all out that time, but it was a simple enough quotient rule that we can kind of see how I pieced it together, right? And I did color code it just so that we can kind of visualize it a little bit better. So this is going to turn out to be x plus a minus x plus a over x plus a squared. The x's are going to cancel. This is going to get turned into 2a over x plus a squared. So put it all together, the derivative here is going to be 1 over 2 times x minus a over x plus a. What we can do here is we can just say that this is 2 times the numerator here. And I can take that denominator and I can whip it back up around. and then it's going to be times, I'm going to put the, I'll leave it here. This is 2a over x plus a squared. So this is x plus a over 2x minus a times 2a over x plus a squared. I can cancel some stuff here. I can get rid of that too. I can get rid of this x plus a. And it gets turned into a over x minus a times x plus a, which is going to be a over this x squared minus ax plus ax minus a squared. Now we get this tangent that we get to work with. Again, we can divvy this up. We can call it h of j, let's do, is going to be equal to the tangent inverse of j. What is the derivative of the inverse tangent? Do we remember? I don't think I do. I may have to check. I should have remembered that. Yes. It is going to be 1 over 1 plus j squared. And in this case, j is going to be equal to, this is a function j of x. It's going to be equal to x over a. What is j prime going to be? This is the function is of x. So it's not going to be, this is basically 1 over a times x, right? 1 over a is not a variable. It's going to be a constant. So it's going to be 1 over a because we have a constant times x and it gets turned into just the constant. Remember, if we think about this again, we say, hey, let's make this a more simple version. If I have the function r of t is equal to t 3t squared, I know that the derivative is going to be equal to 6t, right? Now, what if I have the function r is equal to 3t? What is the derivative of 3t? It's going to be 3. In the same way, because this is a constant, it's just going to be the constant. If that makes sense, then we can put this all together. And we can say that this is going to be the derivative is going to be 1 over 1 plus, now we have j squared here, which is going to be x over a squared times j prime, which is 1 over a. And we're going to have this simplify down into 1 over a plus x squared over a squared times a. I basically just distributed that a. So that is going to cancel like this, and it's going to be x squared over a. And our final answer is actually right here because it's the derivative of this chunk plus the derivative of this chunk. And that is going to be dy dx right here. Okay. Do we see what happened in this whole thing? Awesome. We followed it, we're good. We saw what Philip recommended doing, shifting over that 1/2 because we can totally do that, made our life a lot easier, and we ended up with this answer. All right. I only have one more question regarding simplifying this. Can I say that 1 over a plus x squared over a is equal to a over a plus x squared? And if I can't say that, what did I miss? Okay, my hint is that I can't say this. These are not the same. Don't do that. What we're missing here is that it needs to be the denominator for the whole denominator. So if I really wanted to move that a, I could shift this and turn it into 1 over a is equal to a squared over a, is it not? Because we just cancel out one or the other. So what I'm going to do is I'm going to say this is a squared over a plus x squared over a. And if things have the same denominator, I can add them. So this is 1 over a squared plus x squared over a. And now I can say that this is equal to a over a squared plus x squared. So I can do that. But that is not the same as a over a plus x squared. Notice that we have an additional square. Can I add this to this chunk? No, because they have different denominators. This is x squared minus a squared, and this is x squared plus a squared. So not quite the same, can't add them. All right, that is pretty much all I've got for you. I can stick around for another couple minutes if you guys have questions. I hope everything kind of made sense today.
It's good. Thank you.
Awesome. Thank you guys so much for coming. I hope you have a wonderful rest of your weekend. Thank you.